now, virtually programming. VirtuallyProgramming.com.
So for this high-level shader language tutorial series, I've written an XNA program that allows me to demonstrate these shaders. I'm really kind of making this channel for DirectX, DX11 specifically at this point. But I used to do XNA, and there's still XNA tutorials on my website. And for this example, it just made sense to throw this together in XNA. The code is far more simple in XNA than it is on DirectX. And I'm just now kind of getting my code library built up to the point where I could do this somewhat easily in DirectX. But it was just easier to throw this together in XNA. And but if you're interested in DirectX, don't get disappointed. It's basically exactly the same. Most of this is algorithm stuff that is actually the same in OpenGL as much as or in GLSL, OpenGL shader language, as it is HLSL. But the difference between HLSL for XNA and HLSL for DirectX is pretty minuscule. The biggest difference is XNA doesn't go further. Well, it's based on DirectX 9, which is the reason it doesn't go further than Shader Model 3, although if you do monogame, that's actually running on DirectX 11, which will be the same as DirectX 11, and DirectX 11 will do Shader Model 5. And there's really only one difference between the two as far as the shader model is concerned, and I'll show that here in a minute. But it's basically exactly the same. I mean, the difference between the XNA, HLSL, and the DirectX is minuscule, really. It's very little difference. And for those of you who don't really want to look at the XNA code, I'll go ahead and cover the differences between the two, and then after that I'll proceed to go through this XNA code line by line. But we've got, let's see, should have a textured shader in here. This is going to be what I'm using for the example. And I do a whole video on this here. And then I believe that this shader here, which is actually running for DirectX 11, DX11, is basically the exact same shader. It may be a combination of the blend and the Phong. Let's see. Yeah, I use both. See here, I've got a blend function and a Phong function, and in the XNA code, I do one or the other. But here I just highlight out the one that I'm not using. But it's really exactly the same. It's just I combine the blend and the Phong shader into one shader for this DX11 HLSL shader model 5 shader. Let's see. The sampler settings, I think, are set in the DirectX code. I think you can set it in the code, or you can set it in HLSL. Either way, whether you're in C++ and DirectX or whether you're in C# and XNA, either way, I think you can set the sampler state externally or internally. I have these constant buffers in my XNA stuff, but you don't see them passed as constant buffers like you do in DX11. DX11 I think you pretty much have to specify that they are constant buffers. You don't in the code that I'll show you as the XNA code. Here I'm using a control code. I used padding in my examples, but I'm actually putting this padding space to work in this shader to control things as a parameter. And of course, I'm actually using my vertex normals or vertex colors in this shader, whereas I wasn't really able to use them in the XNA code, and I talk about that in the videos. The normal for the vertex shader output here, this is going to be the vertex normal. You can, in shader model 5, just specify this no interpolation value when you define this part of the structure, this variable within the structure. And that's going to turn off smooth shading if you define it that way instead of defining it the normal way. So that's a lot easier than it is in XNA, because it's shader model 3. You can't just say no interpolation because that's not in shader model 3. And so you actually have to do a calculation in order to do flat shading in XNA, which is a lot harder. Here you just set this and it stops doing smooth shading. It turns off the garage shading immediately and you get flat shading and it's all faceted. It's easier to do here. Looking to see what else is different. Again, I'm actually using the vertex colors in this shader. I named this pixel shader input, but the vertex shader output and the pixel shader input is the exact same thing as I talk about in the videos. So it really doesn't matter what you call it. The input, the vertex shader output and the pixel shader input's the same thing. So you can call it whatever you want. What else do we have changed here? There's no technique or passes. We compile this shader in the DirectX code and not in the shader code. And so the entry points are not defined within this file, really. It's defined, if you go look at the C++ code for DirectX, in that code, I tell it that the vertex shader is named vertex shader main, and that in that C++ code, the pixel shader is named pixel shader main, which is a little bit different than what I've got going on in the XNA version with the techniques and passes. So all that technique pass stuff and the compiling is actually done in the C++ code. It's not done here in the shader. And there's a couple different ways you can compile shaders in DirectX, and that may be largely dependent on how you compile it. But that's really all the differences. I mean, I guess because we were shader model 5, I'm able to say matrix here instead of float 4x4. I mean, that's pretty much all the differences. I mean, all the real code here is identical in DirectX to what it is in XNA. So for DirectX, don't think you're wasting your time to look at that XNA code. It's HLSL either way. I mean, it's shader model 3 instead of shader model 5, but it's really the shader model 3 and shader model 5 aren't that significantly different. I mean, the big difference is where I got to use matrix there instead of float 4x4. And I did all this work in the C++ code rather than doing it here in the shader file. And I don't have to specify that these are passed as constant buffers. XNA pretty much seems to handle that. So that's pretty much it. I mean, all the rest of this code is pretty much identical as far as the HLSL code. So, don't feel like these tutorials don't cover HLSL for DX11. It's pretty much exactly the same. So I'm intending it for both XNA and for DX11. So if all you care about is the DirectX stuff, you may not care so much to talk about how the XNA code is put together, and that's what the rest of this video is dedicated to. So you can go on. Probably going to do this as the first video, and so then I believe the silhouette shading video will be the next video, and you can just skip to that from here. For those that want to stick around and see how the code that calls the shader works, which is written in XNA, so that'll probably definitely be anybody that's actually doing XNA. Let's go through it here. Basically, all the code is in Game 1 CS. It's all here in one file. There's not a lot of code here. This is fairly simple. XNA makes it simple. We've got our model brought in as an FBX from Blender. All the FX files are our shaders. We're only using one at a time. That's basically it over there. So we declare our global variables. Probably don't want to get into them individually here. This controls the camera rotation speed. It's set as a constant, and it's set to what is pi over 2. 2 pi is a circle, pi is a half circle, half pi is a quarter circle, so that's 90 degrees. The initializing the look at spot to the origin. The camera boom length is 10 units. 10 should be about 10 meters. And I set, I don't know why I ended up with a quaternion here for the camera boom direction. This could have been like probably should have been a matrix, but I set it to an identity quaternion to initialize it. I mean, I do sort of know how this happened. Basically, I was throwing this together quickly, and so I just copied and pasted some camera code from another program I wrote, and this is what I got. This is very standard. I think this is what you get when you start a new project. The initialize, I set my screen size to 1280 by 720. You can set it to whatever your screen size is. I set full screen to off because Camtasia can't record in full screen, so I have to use windowed screen to do the recordings. It's also better for debugging to turn it off. You can turn it on for a little bit better results, but it's tough on debugging if you've got a bug in it set that way. And then I have to apply the changes made there. Define a projection matrix. Pi over 4 or a quarter of pi is a pi is a half circle. Half pi is 90 degrees, and quarter pi would be 45 degrees. So that's a 45 degree angle there. I ask the graphics device what the aspect ratio of the screen is currently set to, which I'm thinking should never change. And you know, unless you get a new monitor or something. Anyway, so that just asks it what the aspect ratio is, and then tells it what the aspect ratio is, which in my case is 16 by 9. And then the near clipping plane distance and the far clipping plane distance in meters. I set it wide open, so basically everything draws. The model's world matrix initialized to an identity matrix, which is an empty matrix, so it's at that point exactly like it was supplied in the model file. And then the initial camera position as X, Y, and Z. Here is where I tell it which shader to use. I've got everything. I'm only using, you can only use one shader at a time, so I comment out all the others and uncomment them as needed. Here's where I load the model, the FBX model, which it doesn't have an extension because it's not actually loading this. The FBX file gets read, and then it compiles an XNA binary file, which is FBX, or I'd be able to think of it if I wasn't trying, an XNB file, I believe. And it compiles that file, and then it uses that compiled file, which is why the extension is not FBX, to load the actual model from then on, which is a lot faster than trying to read out the FBX. This is for animation, or rigid animation, really. Yeah, I think theoretically you could use this to make the eyeballs move, but this is probably not the way you would do it anyway. You only need this if your model has multiple, has submeshes. If it has multiple parts, then you have to do this. But if it's all one mesh, which I think this actually is, probably, then you don't need that. I wonder if it'll even run without it. Nope. Guess again. Yeah, it's not happy about that. So I need to fix it. Nothing in unload content as usual. The update, the camera rotation rate and radians per frame, that's determining how fast the camera is going to rotate, and keeps it running at a constant rotation speed, regardless of the frame rate. If the frame rate slows down or speeds up, the escape key on the keyboard will exit the program. This is all camera controls. The left, right, page up, page down buttons move the camera around, and these are actually fairly simple the way they work. Like page up and page down, just take the camera position and move it by these coordinates, X, Y, Z. So page up is going to add to the Y value by that rate, as long as that page up is, every frame, as long as the page up is held. And so basically it'll just move the camera towards the sky, and page down moves it down towards the ground. And then left and right actually rotate around the model. And that camera position that's been changed gets normalized just in case it got denormalized. The camera direction, not to be confused with the camera position. Oh, okay. So it takes the camera position and turns it into a normalized version of itself, and then sets that as the camera direction. So the camera direction is pointing in the direction of the camera position, and then we make it into a 2D vector on the XZ plane by getting rid of the Y value. And the up and down keys, I think, actually move in and out towards the model. Here we set up the view matrix, very straightforward. The camera is at the camera position. It looks from the camera position to let's see. It's looking at whatever the camera's height is. It's going to look at that spot at the origin. So X and Z are at the origin. The Y is actually at the height level of the camera. And then we get to use the vector 3 up cheat because it works here. And that's just a vector that points up. We clear the screen in your standard XNA cornflower blue color for the background. Here we use that stuff that I said we were going to get back into with this bone stuff. We're looking at our mesh, the Professor Zombie mesh, and we're looping through every sub mesh, and and then we're drawing every submesh individually. We're telling every submesh go draw itself. But in between that, for each submesh, we go through its effects, which are the shaders. The shaders are actually stored in each model part. Each model part or submesh has a shader stored with it. And so we have to supply values to that submesh's shader. For every submesh, we have to pass it the three matrices, the projection, the view, and the world. We have to pass it all the parameters of, that need to be passed to the shader. Then we can draw each part after that. Let's see, before I dig into some of this other... Yeah, that's all the code, but I kind of skipped some things, so let's cover what I skipped. The world matrix, we're combining the zombies world matrix, which is set to an identity, so it's empty, and that makes this pointless. But we're using these bone matrices. And let's see, we got mesh, parent, bone, index. That was the part that I skipped, sort of. That's right here. Professor's bone world matrices. We set up this array to put the bone world matrices in. So what that means is each part has its own world matrix, which describes its position and its orientation. And here we set up this array to put each of those matrices in. And then this copy absolute bone transforms 2 fills up that array with all the matrices of the model. So I think this is in the default position for the model, and it saves all those default positions for every part. And there was a time when I probably could have told you a little bit better exactly what that does when I was building my model class. And I forget off the top of my head exactly why that's done that way. But it's looping through each piece. And then here for the world matrix, we're using that matrix out of the array of matrices so that it's the correct matrix for this part. And then I'm combining it by this model matrix that's the world matrix for the entire model, which theoretically should allow me to move the entire model around in the scene and all of its parts together. The ambient light color in the actual shader videos, I'll actually talk about how this is working a little bit more, but the ambient light color is basically the color of your shadows. It's the silhouette shader color. It's RGBA color, red, green, blue, alpha, where the numbers are between 1 and 0, and 1 is 100%, 0 is 0%. So that's 30% red, 30% green, 40% blue, and 100% alpha or transparency. And then for the diffuse light color, which is like your sunlight color, it's like 100% red, 100% green, 80% blue, and 100% alpha. And I covered this again in the videos, so I won't go into too much detail there. But the direction, this is a vector normal, although this one is not normalized like it's supposed to be. But I think, well, anyway, it seems to work out. It seems to work itself out anyway. But this is just, it's a vector normal that describes what direction the light is shining in. And of course, this is a 3D vector where the X, Y, and Z values are the position of the head of the vector, the head of the arrow. The tail is always at the origin, which is 0, 0, 0, so you don't really need to define that. Here I do a little bit of a trick. I need to know where the camera is at. For the shader, you'll see how that's used. But I need to know where the camera is. And so I want to ask the view matrix where the camera is, because the view matrix is really what stores the position of the camera, I don't want to store it twice. I just want to ask the view matrix, where's the camera at? And the way to do that is right here. I create a vector 4 to store the value in. I initialize it to 0. And then I take the view matrix and invert it and store it as a new matrix, the inverted view matrix. And that is necessary because it's a view matrix. The view matrix is basically a world matrix, except for it's inverted, and I basically explain that in the matrix videos. But it does everything backwards. So to get it to work like a world matrix, I need to invert it first. And I don't want to permanently invert it. I just want this inverted version here. So I create a new matrix called inverted view and put the inverted view matrix into it. And then I can use the translation function of the matrix to get the position. Translation will give you the position out of that world matrix, which I'm now treating the view matrix as a world matrix, and I can get the x, y, and z coordinates of the position of the camera right here and store them in my vector 4 that I created, and then I set the fourth value to 1, the w value, because it's a position, it's just always going to be 1. I'm not even sure that that's even going to matter. If you set that to 0, if it's going to care. Yeah, it doesn't even seem to care. But technically I think it's supposed to be 1 because it's a position. And I think if you look through the code, it's probably not even using that value when it comes time. Yeah, but all you're really doing is passing it the position, the 3D position, the 3D coordinates of the camera position. And then the color map is the part that I really skipped. This is kind of complicated, and it's because of the way XNA's model is set up. This is your texture, right? So the texture is actually stored in the model. And let's look at that. So this is your FBX code, and it's ugly, and it contains a ton of data, most of which you don't actually need. I need to find, I'm looking for the texture, and you can see there's a ton of info in here, and a lot of it's junk. That's why it compiles this down to something that loads efficiently. Somewhere in here it should have the Professor Zombie texture. Let's look for texture. Guess again. Let's look for zombie. There we go. I think it's Professor Zombie normal. That's the normal map that we're not using. So it tells it which normal map to use. It's just our shader's not set to use a normal map. Okay, here in the materials, the eye uses the material eye color PNG file. The main texture is the Professor Zombie norm texture. Let's do a search on that. Somewhere in here, I'm thinking it actually maps to an actual, there it is, PNG file. So it's telling it which texture file to use. No, don't save anything. I don't want to mess it up. telling it which texture file to use in the file. So I don't have to tell it what texture to use. It just knows because it reads it out of the file, and the texture is going to be included. So here we have the texture files, the normal file. I've got really all the different maps: the specularity map, the color map, the normal map, the eye color map, or an eye color and eye color emissions. All of that's here, but all I'm really using, I think, is not that one, but probably the color map. Let's open it up and take a look. Yeah, there's the color map. That's what it actually looks like. So that's what I'm using for texturing, and I'm just not using the other maps. But anyway, in fact, I don't think any of the others are actually brought in by XNA's model class. And that's kind of the problem here, is that we're using XNA's model class to do all this work, which is great because it does so much for you and makes this easy. But it's also bad because it doesn't know how to use normal maps and so on and so forth. Although I think I figured out a way to kind of trick it to work, which is basically to do what we're doing right here, because it stores every shader, every effect with the model part, with the piece of the model, which in this case I think the eyes are maybe separate meshes, separate pieces. And so it would store a shader for the body and then a separate shader for each eye. And it uses basic effect when it stores that. And it's kind of cool that effect and basic effect must inherit from the same parent or something, because they're kind of somewhat interchangeable. But the bad part is they're significantly different, especially when it comes to textures. Basic effect has a texture parameter, effect does not. And so we need to use effect so that we can use our shaders. We don't want to use XNA's built-in shader, basic effect, because the whole point is to use our shaders. We got to use HLSL, which means we need to use effect and not basic effect. But effect doesn't store a texture as far as I can find. And so when this model loads in, it stores basic effect, the built-in shader, with every part. And we need to go through every part, which is what these loops are, and reset the shader to be our shader. So it really starts here. The part is this part of the mesh. We've got each sub-mesh and then each part of the sub-mesh. I'm not fully understanding the difference between a sub-mesh and a part. There's apparently some sort of difference, but in the way this turns out working, I'm not... The difference may be kind of superficial, like maybe a part and a sub-mesh are really the same thing. But anyway, here, let's see, on this line, we're taking the effect that's currently stored in that part and storing it into our basic effect, which is temp. Now, I think we have to actually convert it to a basic effect and tell it that this effect is a basic effect. But we're making a copy of it, and then we define a texture 2D called color map, and we take the texture from the basic effect that is supplied with the model, and we make a copy of that texture in our color map, a temporary copy. Then we take our shader, HDLS shader, which is our shader that's loaded in, and we clone it. We make a copy of it because you can't just say equals to make a copy. You got to use clone, and so it makes a copy and stores it into that part's shader, that part's effect. And so we've just lost all the texture information at that point. If we did just this line, it throws away all the texture information, and we have no idea what texture was originally supposed to be used by that part, which is kind of crazy. But that's what all this code is here for, is to fix that problem, which is since we made a copy of the texture, color map is the texture 2D, we have that texture because we saved it. And we put it into that parts shaders tag. The XNA model class has tags at several positions within the model class, and from what I've seen, they're actually designed to basically be used like this to store value with the model, whatever you want. And I think it's like an object data type. It's like a generic data type that you can put pretty much anything in it. So here we're putting a texture 2D in it. You may want to build a class or a structure so that you can store multiple values in each tag, because there's just one tag like per part or whatever. And so here we're wasting it on one value. But if I were to put this color map and other things into its own class or into its own structure, then I could put multiple things in the tag and store them, because I don't think the tag is just an object pointer. But anyway, that's how we pull the texture information out of the model class, then assign our shader to that part, and then put the texture back in. We don't have a texture value in effect, so we can't put it back into the texture, but we put it into a tag where we've at least got it together with that part of the model. And then when we go to draw, where's it at? Oh, it's very last line. Then when we go to draw, we pass the texture as a parameter to the shader. We pull it out of the tag, and the tag is generic, so we have to tell it, hey, this is a texture 2D, so that it knows what data type it is, mainly because this parameter wants this data type, and so without it, it won't work because it's looking for a texture 2D, and then you try to pass it this generic object, and it's like, I don't know what that is, and so it'll just blow up. So if you tell it it's a texture 2D, then it'll accept it and load the correct texture into that parameter. And so that's what all that kind of convoluted code is all about. But I mean, in addition to the color map, the texture here, you could have at this point made a structure that holds not just the color map, not just the texture, but also the normal map and the specular map and any other maps you want to have. And then you could down here read those as parameters into your shader. So you'd have to go another step further, because tag would actually be a structure, and so you'd have to dig into that structure and ask for the color map, and then ask for the normal map, and then pass those as separate parameters as textures. But that's really all there is to this program. I mean, it's doing quite a bit with very little code. When I want to switch in and out a shader, I just comment out the one that I don't want, and uncomment the one I do want, recompile, and run it, and it'll switch shaders. And that's really all there is to this code.